Hello everyone and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed in order to help scientists discover the world around us. Today's topic, X-ray microscopy. What's an X-ray microscope? Well, we combine micro-CT hardware with specialized software to create a complete imaging solution. It's basically the equivalent of being able to take three-dimensional volumetric pictures of any sample across a wide range of different materials. Now, more specifically, we want to dive a little deeper today. We're going to go for the maximum resolution with our nano-tomography solution, the 2214, which has just been upgraded with brand new detectors, the CMOS. In fact, scientific CMOS, so a whole different level of detection technology. Now, to learn a little bit more, let's start off with a video, and then we're going to head on over to the studio and talk with one of our experts. And hey, thanks for joining us. Here we're back in the studio, and I am joined by Dave Sampson.
Morning, John.
All right, welcome back, Dave.
Thanks. It's been a while.
Yeah, it's been a little bit of a while, but I think the last time we talked about XRM, it was actually the CMOS detectors on the 1272, which is our benchtop high-res. Huh?
Yeah, we had just upgraded the 1272 with the new scientific CMOS detectors.
And we've seen just an explosive growth in terms of the different applications that our people are looking for and the way that they're using XRM ever since then.
It's been a great new system to work with.
So CMOS is kind of the new detection technology. I know in optical cameras like the ones we use to shoot our show here, there was that transition from the older technologies into CMOS.
Right.
And now we're seeing the same thing with our scientific instruments.
Yeah, absolutely. We're transitioning everything from CCD to CMOS.
Okay, and what do CMOS detectors bring to the game?
A couple of things. Really, the biggest thing for my point of view is they're quieter. They're lower noise.
Okay.
Which means you can take fewer images to do averaging. So on an old system, you might do 3, 4, 5 images, and then average that to get a good image. In this system, we're doing 2 max.
Really?
Yeah, it's doubled.
Yeah.
I mean, it's half the speed, half the image time of the samples. Also, you have a better range contrast. So your contrast is a lot sharper with these images.
So you're able to see details
right,
that you
so
weren't
you can
able to see
scan faster
before.
at higher resolution with these detectors.
All right, and also, I mean, something you get is a little bit more dynamic range.
Yeah, absolutely,
things, right?
And that's kind of what we're talking about with the contrast. Because you get a better dynamic range, you get the dense particles show up nicer, and the low density areas show up better, all in the same image, instead of having to tune in one or the other. And actually, another thing is we were seeing less scattering effects as well. So there is scattering off some objects, and we see a lot less. So the image quality is a lot sharper.
And an example I like to use when I'm thinking about this and imaging is, say, TVs. So it is almost like going from one of the LED type TVs to one of these OLEDs where that background is just nothing.
Blacks are black, yeah,
yeah,
absolutely.
the subtlest detail can then stand out. And oftentimes, right, it's that difference, it's the heterogeneity that makes the difference in every single sample.
Right, exactly, heterogeneity, exactly. And when you do get very similar dense materials, the ability to see the difference between very similar materials is so much sharper in this.
All right, so now the other part of this equation, though, it's not just about the detector. Of course, that's the new thing.
Right.
But we also did some upgrades, kind of infrastructural upgrades, a little bit more stability in the overall system.
Correct.
So if we talk about that 2214, what differentiates that from something like the benchtop 1272?
Well, for me, the 2214 it's the flexibility.
Okay.
So on the benchtops, we have a product line for various applications: high res, high speed, general use, large sample volume. With the 2214, you have all of that built in.
Okay.
Like you showed in the video, you get the larger field of view. I can do quick imaging on large samples, but then I can go down and I can get really, really high resolution on samples. I can do it all with one instrument.
All right, and then functionally, we saw that there's some different components of it. So we have a high stability base, right? So that's actually a piece of granite, right?
Yeah,
and it's floating
big,
on an air table.
Yeah.
So that keeps everything just nice, steady. You can collect long time, and you're not going to have drift.
Right.
And then the other part of that equation, the source.
Yes.
So here with this source, we're able to optimize the filament for either high res or high power.
Correct.
So then we have that ability to move the sample.
Right.
Right?
Yeah. So.
Okay. So geometric magnification.
Geometric magnification, exactly.
All right. And in the 2214 CMOS, we actually call it Gem Plus. So geometrification plus, now we add in the detectors to that equation.
Right.
So now for some people out there who are new to XRM, what is geometric magnification all about?
Well, geometric magnification is the ability to, so when you're scanning an image, you bring it closer for magnification, farther back for higher field of view.
Okay.
So that you can do that all in one sample. So quite often in an experimental setup that I'll run, I'll take my sample, move it back, get a big overview, see what my data is, and then progressively move my sample closer without doing anything, just moving the stage closer, and it allows me to get higher and higher magnification.
All right, so it's about that ratio, right? We put the sample closer to the source, so you have a tiny sample to source distance, and then you have a really long source to detector distance.
Right. So magnification is source to detector divided by source to sample.
All right. So the part of that equation, though, then is the actual sample size, right?
Correct.
So your resolution depends on the sample size.
That is correct, because the smaller the sample, the closer I can get to the source, meaning my bottom is a smaller number, which means my magnification is greater.
All right. And so in that traditional geometrification, that's kind of one of your limits. But now what we add on to it, we plus it, is by offering those detectors.
Correct.
So now we have, we said we have 4 detectors in total.
Correct.
4 detectors in total. Not 4. 4. Okay. Or I guess if we're German, it would be like 4, right? Yeah. Back in contact. So in Belgium. So in terms of those detectors, let's talk about that a little bit. So the first detector, that's the big one.
Right.
Now, that's a flat panel detector.
That is a flat panel. So it is standard CMOS.
Okay. Okay. And then now we go into the detectors and we have a standard sCMOS detector, and that kind of is a good balance point.
Right. That's the standard, and that is the same detector we use in the 1272. It's a great general all-purpose detectors. Big enough field of view, high enough resolution, and because we have the geometric magnification, it gives us a pretty large range of parameters for most experiments.
Yeah, and that's that big benefit now, because we've decoupled a lot of these resolution effects. You could take any detector you want, and then by moving the sample, and even on these things you can move the detector, you can get the right balance of field of view and resolution.
And and one of the things, the big benefit I find is because you have a spectrum of samples, of parameter settings, large field of view with the large camera, the high field of view, or the small field of view, high res with the high res camera, I can then fix my resolution to where I want it, and then I can choose a detector and a distance so I can maximize my collection efficiency.
All right.
So I can even drop my scan times even lower by optimizing those effects.
So now we talk about standard CMOS then. So now you can go either a little bit bigger or a little bit smaller, huh?
Right.
So what do we gain there?
Between
So go into the bigger detector.
Oh, the bigger detector would be, you think of everything as photon flux. How many photons can I collect? So if I have a bigger detector, I'm actually getting more of the X-ray beam, so I can collect faster.
Yep.
Okay?
And then when we go down to the higher res detector.
Right. Now you have smaller pixels, which allow you higher resolution. A little bit of hit on time.
All right. And again, you can take any of these detectors, move a little bit closer, move a little bit farther. You're going to get more field of view, more resolution. And this is all just a continuity stream. You find the right setup for every single sample. Now, speaking of samples, I know you've brought a few examples for us to look at today,
this is just some of the fun stuff I've done since I've got my instrument about 8-9 months ago.
Yeah.
So
if we take a look here at the screen.
Why did that pop up? So this is a.
What are we looking at?
So this is food. This is a cheese, crunchy cheese.
Crunchy cheese curl thing. Okay.
Yeah, and I really love it because it really highlights when we're talking about the lower resolution, or the lower resolution, the lower contrast. This would have been tough with the CCD to really pull out all this detail information. Let me pause this and pull up the just a 2D cross section, and I really love this because this is the cross section through the crunchy cheese puff.
Okay.
But you see all the pore structure. You see the thickness of the walls of the bread, basically, and you see oil inside some of the pores.
The contrast in the color there is actually oil?
That's oil inside the cheese puff. Yeah, exactly.
So it's trapped when they fry it. Some of that gets trapped, huh?
And then you'll see that the structure of the outside is a little bit thinner.
Yes.
And then there's larger pores on the inside, so that's you bite in and it's crunchy, but then it's soft, it's chewy, and then these bright spots would be the orange flavor dust on the outside.
Okay. So now in terms of analysis, we've kind of said, you can see, but my understanding too is that we do offer software that allows you to quantify everything, right?
Absolutely.
Okay.
So we have our CTN, which is our CT analysis package, which is a very comprehensive set of tools to analyze this data set. So for something like this, I would do like wall thickness, and it really is just a push button that will give me the wall thickness for the entire sample volume. I can also do open pore versus closed pore. I can so all
calculate the amount of dust on the outside, stuff like that.
Exactly.
Okay. So it's kind of it's one of those things where the sky's the limit in terms of the information you can get, but that information is so important for this process.
Oh, absolutely.
To make it just right.
Right. Yeah.
And that's, by the way, this software. That's why you call it an X-ray microscope. So there's a lot of CT systems. There's a lot of micro CT systems. You got to combine not just the tech. You got to get the software.
Correct.
Now you got a microscope.
Right. It's easier to make a microscope than it is to make good software.
That's right. So in terms of then this particular product, this for food, though, is not just the only example, right? We see it across the spectrum. We're seeing it in not just food safety. We're not just talking about metal particles or shavings.
No. This is R&D for food. The mouth. What's the taste? How does it feel in your mouth?
Yeah,
that's what they're tuning here.
And if somebody accidentally changed the thermocouple or adjusted a temperature, bam, you would see this.
Or even like an oil changes between two batches of oil. You're going to see that in residual oil residue. You're going to see that in the structure of the food.
Yeah. So it's all about having the right quality of product. in addition, right? It's not just, does it work, does it not work, things like that. It's how good is it, right?
Right.
So now we've got another example, though, right? That takes us out of this, out of
Sure.
the food area and into something different.
Yeah, let me pull up. So this is a print nozzle for a 3D printer.
Yes.
And this is actually a ceramic. This is alumina. Alumina is actually very difficult because it's a very dense material.
Yep.
But yet, we are able to get the structure, the grain structure of the sample.
And is that what we're looking at when I see kind of that little spottiness around the outside?
Exactly.
That's not noise in the data, huh?
That
That's
is not
actually
noise. That's actually the structure of the material. It's a high density and the low density information in the sample. And so here you can see it in cross section.
Okay.
And so you get, a lovely view of all this, and you can see all the information. There's a few voids sitting in here.
Yep.
And there's actually a large crack.
Really?
Yeah, so you can see
wow.
right there is this large crack to the material. Yeah, and doing a visual inspection, you wouldn't see that. The only way
Right.
you would see this is to cut it open, and you can't do a 100% inspection where you cut open all your samples.
Well, I mean, even that last example, the Cheeto, right? I mean, imagine before having this technology, taking that and trying to cut it, right?
Oh, yeah, absolutely. And that's what they're doing. They would cut it in optical, or they would take it and code it and do an SCM image of it. And the amount of time for sample prep is less than, is more than the entire experiment here.
And it's the integrity of the sample. Even this one, I can imagine if you had a crack like that, and then now all of a sudden you're trying to grind it down, cut it, it might fracture, it might change condition, you might even miss
Right, and in fact,
crack.
and some of my customers, they said the act of trying to prepare the sample for imaging.
There we go. Oh, there it is.
There's the crack.
Wow.
Yeah, I've
Clear as day.
A couple of customers have said the act of preparing the sample actually generates more damage than the actual is there, more particles. So they can't really prepare samples for the SCM because it damages them to a point where they're not really sure what's there. Yeah, but that is so great right there.
And here I would imagine now this is going to cause a lot of drag on your filaments as they're going through there.
Right.
You might get a little bit more stuck filaments, but also the print quality overall is just going to suffer because of it.
And as you go through heat cycles, you're heating up and cooling it down. That's only going to take that crack and make it bigger.
Yeah.
So this would be the failure point. This eventually would crack at that point.
And I could even imagine that if you're using some filaments that are a little bit more abrasive, you might want to use this technology to occasionally check filaments, or check the nozzles, see how long they're going to last.
Oh, absolutely, yeah,
right?
because it is completely non-destructive. I can take it out of my system, I can measure it, and I can put it in. And you can also then check over time. You can see the wear, you can see the damage, you can see if there's any problems creeping up on you.
So now, I also know with these, another common material would be brass.
Yes.
That these are made out of. Would we be able to image brass with this?
Brass is tough.
It's going to be a little bit tougher to get through?
Yeah, brass is a little bit tougher. Maybe a few millimeters of brass, but if you hand me a big chunk of brass. Our systems really aren't designed for that.
Okay, so a small nozzle, we might actually be able to see through it. If you got anything that's too big, then, then you hit a limitation in terms of absorption.
Right, and like I said, I always go back to photon flux. Because the brass is
very
so high
attenuating.
dense. Yeah, very attenuating. You're not going to get many photons through it.
So how high of an energy can we go on this machine? Because the 2214 goes a little higher than the benchtops, right?
Right. The 2214 goes up to 160 kilovolts.
Wow.
Power.
Okay, so quite a bit of power to punch through the samples too with this machine.
Right.
All right. So here, now we talked about 3D printing. And of course, the stuff you print, we didn't even really touch on that. But man, like the applications are endless there.
Oh, absolutely, yeah. 3D printing is great. There's so much you can see because you get a 3D printed object and you go back to, well, did I print what I was supposed to print?
Yeah.
Right?
Yep.
So you can actually compare the 3D printed object back to the CAD files to see what you did.
Really?
But then you can go a step farther and I can look at what's inside. Did it print correctly? Do I have any faults, any cracks on the inside? Is there any residual material left inside? So if you're printing a thin pore, well, what's inside? There's no way of inspecting that.
Yeah, that's true.
And there's also some work being done, like can you connect a 3D printed object back to a 3D printer?
Yeah.
which is really interesting.
Oh yeah, I mean that's important these days, especially with that idea that you can basically print anything you want, right? I mean,
Exactly.
And as the materials start to push the limits for home use, right? I mean, it used to be, oh, you can do just basic plastics and these cornstarch-based plastics, but now you can get into metal prints and things like that.
Exactly, and so there's a lot that can be done with 3D printed objects.
So now I think you brought a third example, right?
I did. So this is a 500 nanometer resolution image. So voxel
That's a candy cane.
That is exactly.
Because Christmas is coming. That's a candy cane, right?
It's a jelly roll.
It's a jelly roll. There we go.
It's a jelly roll.
Thanksgiving. There we go.
So this is actually a watch battery.
Really?
Yeah.
Okay. So what we've got then is we've got these separation layers.
Right.
And then we can, wow. So in the white, I can actually see the little grains of the material. Huh?
Right. You can actually see the grain structure of the material. You can see the electrodes. You can see the separation. So again, this is 500 nanometer voxel.
Yep.
So 1 micron-ish detection rate. So that's what a resolution is. So, and this is kind of at the lower limits, like of the X-ray source. The X-ray source will do. We say it will do 500 nanometers.
Okay, and that's kind of also based on the standard. So as a manufacturer, we want to make sure we can really confidently say this standard. It's measured to this standard. Here's the 500. Here's our cross section cut through it.
Correct. When we install a system, we verify it's running at 500 nanometers.
But the reality is,
I can do a little bit better than that.
Yeah, we can likely get a lot better than that.
Yeah, we like to do a little better. Yeah. And there's a couple of situations. Like I said, you can get 400 if everything lines up right for you.
Yep. And even this battery. If you want to see an even better image, go ahead and take a look at our new brochure for the 2214 CMOS, and we have even a higher res version of it.
Oh, excellent.
Yeah.
While the resolution of the system is 500 nanometers. That is a function of the X-ray beam.
Okay.
So the X-ray beam, you can get down to about 500 nanometers at low voltage. Our voxel size, our ultimate voxel size, is about 60 nanometers. So I can oversample that data set. And there have been occasions where I've looked at 200-ish nanometer objects, but they're separated by a micron.
Yeah.
So while I'm not claiming I'm resolving, but you can actually see them. You get really nice data, sub-micron.
So you mentioned this word voxel.
Yes.
And that might be something new to the people out there. So could you describe to us what a voxel is?
A voxel is just a 3D pixel. We all use pixels. We know everyone has a knowledge of a pixel. It's a voxel is just a 3D equivalent.
Okay, so we take the 2D, like we're all watching the TV right now, or the computer screen, and then you're going to also stack them the other way.
Exactly.
So volumetric
X, Y, Z.
Okay.
And then a fourth.
And when we talk about resolution in one of these machines, we can talk about voxel resolution or kind of real resolution.
Correct.
Okay.
Correct. And just in all microscopies, there's a resolution which is defined as can I see what is the smallest object two objects I can define next to each other
that you can resolve from each other.
Right. And what we claim, so for in a XRM, it's basically twice the voxel size.
Okay.
Or twice the minimum resolution, or the X-ray diameter.
So in the voxel size, that's something out there that you'll see in a lot of specs. You'll see, okay, well our maximum voxel or minimum voxel is
Exactly, and voxel is just a number.
And it's important.
Right.
It's important that your voxel size is lower.
Right.
And you do want to oversample slightly.
Right. You want to match. But you want to match your voxel size to your X-ray diameter.
All right, and that basically just takes into account the geometric magnification plus the size of the pixels. Okay, and then the real space, like you said, essential there is the source spot.
Right.
Okay, and that's one of the things where the 2214 really differentiates, is having the tiny spot.
Exactly.
Okay, and then in addition to that, we have that effect of the geometric magnification. You also have the effect of the sample stability, right?
Correct.
So, and on this machine, the sample actually floats, huh?
Yeah. So it's an air bearing for the rotational stage. So it gives you nice, clean rotation without any wobble or shake, and very, very repeatable angular motion.
All right. So here again, 2214. It's not just about what I'm hearing from you, it's not just about the highest resolution. It's also about that capability to be able to get the right resolution, the right field of view for every sample.
Correct.
Okay.
Ease of use too. It's a very simple machine to
Just
run.
walk up, put it in.
Walk it in, put it up. Yeah. Years of doing other microscopy techniques. It's really nice to pick something off and set it up there, and in a few minutes you're running.
Yeah, hit the button. You don't have to worry about like a big vacuum pump system or something like that going down.
Exactly.
Yep. All right, so we do have some questions that come in, but if anybody out there right now has any questions, you can type them in, and we're going to answer them immediately right now. Otherwise, you can always send them in to live.events@bruker.com, and then we'll answer those back. So the first question that we have that came in, it came from Marion, and she is asking, I have a 2214 already, so good job getting the 2214. Can it be upgraded to these new detectors?
And the answer is absolutely.
All right.
Yep. We have a in-field installation package that you can just exchange all of your CCD detectors for new CMOS.
All right. So yeah, and you can at that time you can decide. I just want to throw in the standard one, the high-res one, whatever you like.
Now you do have to swap out. You can't have some CCD and some CMOS.
Okay.
It got to be all one or the other. As you mentioned earlier too, on most systems there is a cutout in the back of the instrument.
Yep.
If it's not there,
okay.
You're one of the 10 people in the world that.
So it's there is the whole gantry that we've kind of adjusted to, the part that's holding these detectors.
Right,
and
it's newer, smoother.
Yeah. All right. Next. Oh, and by the way, if you do the upgrade, you'll get one of those little stickers too.
Oh
CMOS
yeah,
Edition. That's always really important to get on your machine. So from Lucas, what resolution can I achieve on a test cylinder of cement with nanotubes, which is 2 inches in diameter and 1 inch in length?
So the bottom line is, it doesn't matter what your detector resolution is, what your system is. If you're trying to look at the entire sample, the easiest way to do it is you take the sample and you divide it by the number of pixels in your detector. So in this case, 4,000.
Okay. So we got
2 inches.
we're going to try to do math.
5 centimeters. We're talking about 12 micron voxel size, so 25 micron resolution.
Wow.
So
wait, can you say the equation again, Dave? I think I missed it.
So you take the sample,
okay,
divide it by the number of pixels, like one side of the camera.
Yep.
So in this case, we have a 4,000 by 4,000.
That would be the high res.
The high res and the large field of view.
Okay.
The large field of view and the standard. The high res is 5,000 by 3,000.
Okay. So if we're using the standard.
We're using the standard, which is what I would do with this.
All right.
So it's going to be 4,000.
4,000 pixels.
So you take 2 inches and divide that by 4,000.
All right. So we took about 5 centimeters divided by that by 4,000.
12.5.
12.5
times 2.
Times 2. So 25 microns. Okay. There you go.
Now, anything smaller than that, you're not going to see. So if you did have, these carbon nanotubes, which are nano scale, you're not going to see them.
Oh, yeah. We're talking, though, a 2-inch cylinder.
Yeah, we're talking. And actually, I do 2 inches all the time.
Okay.
It's a very common samples standard. Yeah. And a lot of work is being in cement these days. You're trying to come out with cheaper, less environmentally damaging ways of creating cement. And so cement is a very, very big topic right now.
So then we're just out of luck.
We're
not out of luck. You just make a smaller sample, right?
You do, yeah, actually. Okay. If you want smaller, yeah.
Yeah, so if we were to shrink that down to like a centimeter sample,
right,
then we're going to get 5 times better resolution?
Yeah.
Okay, so there you go. So you just, smaller sample, you can put it closer.
Yeah.
You could also use the higher res detector.
Right.
Right? And then you can also move the detector far back.
And you can also do a center cut. So you don't have to, just because you have a large object doesn't mean you have to image the entire object. You can image a subset of that object.
That is true, as long as it doesn't physically.
Correct. Hit the sample.
I bet you've never done that, Dave.
Never.
All right, and then Francis sent in a question.
But I want to add, all of our systems do have crash protection.
That is true. That is true.
And I have used it.
You've confirmed it works. Francis, what is the ultimate resolution of the system?
We kind of discussed that. It is a function of your X-ray source.
Okay.
So the X-ray beam defines the minimum voxel, basically.
Yeah, yeah.
So if your X-ray source is a 2 micron or a 5 micron source, that's going to be, take that multiplied by 2, and that's going to be really your ultimate resolution. So on this system, with a tungsten filament, you have the option of tungsten or lab 6. So a tungsten filament, that is going to be 1 micron.
Okay.
And for the lab 6, it's going to be 500 nanometers.
And the beauty of this machine, though, is that you can exchange them, right?
Yeah, it's very trivial. You have a lovely video on
yeah.
how to do it.
You can always go to the website, bruker.com/SKYSCAN2014. There's a nice little video there of changing the filament. It's such a simple process. It takes like 2 minutes. You know, the thing about ultimate resolution is funny, though, because I think oftentimes, we get this question a lot at shows or at talks, whatever we do, you know, how good can you get? But then they tell us about their application, and the reality is the application is far above that.
Absolutely.
In terms of resolution.
Right.
Yeah.
Every day.
Yeah, yeah. It's always, of course, it's always good to know where you can get to, but that's important whenever you're leveraging a solution. Is really, you know, define what you need, and then define the zone of what you want.
And we, because we have benchtops and the 2214, you may not need the 2214.
That's right. That's true.
I mean, the 1272, you know, has the same detector as the 2214.
Yep.
So if you have a very certain size that you need to run every day, that might be your best option.
Yeah, and that can go both ways. So
yeah, absolutely.
Yeah, I mean, sometimes, right, we have people come in, they have a sample, we go, you know what, you'd actually be better served with 2 benchtop machines. You get twice the throughput, you're good to go.
Right.
But then other times you have somebody come in and they say, well, my needs today are this. But they say down the road I could see a need for that. Nice thing with 2214, you can add the detectors.
Exactly. I actually was going to throw it in. It's like you could put in what you need right now.
That's right.
And then just add as you go along.
Yeah, and then you can kind of grow that system, eventually get up to the 4 detectors. But you could start with, you know, flat panel. You could add on standard CMOS. Hey, I need a little bit resolution for the next experiment. Let's put in a grant. Let's get the high-res one. Now let's go for the other one. And then you can add in the stages, right? You got temperature stages, all kinds of stuff.
Compression stages.
So a lot of stuff to add. All right, and we've come to the end of the question. If anybody doesn't have any questions, though, moving forward, if you're watching this video later and something just comes to mind, send them on in, live.events@bruker.com. Thanks to everybody out there, though, for joining us today. It was a great discussion about the 2214 CMOS. If you have any questions, you want more info on it, go ahead and send that email in, too. Thank you, Dave, though, for joining us.
Thanks, John. Thanks for having me back.
It's always hard to pull you out of the lab. I know you've even today we've probably just piled on the workload.
Absolutely.
So these XRM system, it is really, really changing things, I think, in the material science world.
It's a great product.
Yeah, it's giving vision, I mean, where before there wasn't any. And so it's one of those technologies that you jump on it today and you're going to really be a leader in that field. So until next time, though, go ahead and keep your signal high and your background